Okay, cool. It's recording on here now. All right, cool. Let's get started.
How many iterations did it take to get the QR code to work?
It took a lot to get it to that main point, but it took like 5 to, like, once I got the model actually working to get it. But it was only 5 on that prompt. All the other prompts I tried were bad, so probably like 100 in the end.
Yeah.
Yeah, took a while.
It's a lot of effort.
Yeah, but I wanted to get it working. I thought it would be cool. Okay. Let's do diffusion. All right, cool. Go ahead and grab some pizza and then start talking about diffusion.
Pizza's so awesome.
Best part.
In general, or is a lot?
Just in general.
Yeah, it's a superfood.
It's wild that it exists. I'm very happy that
Free
it
pizza
does.
is the
I'm
best.
happy we have pizza in this world.
It's a cute form of
Free pizza is awesome. Very cool.
Like, if there wasn't pizza, what would the staple party food really be?
Nothing.
Yeah.
Chicken wings.
Wings though?
It's not the same.
The pizza's like just the right amount of messy,
Mm.
you know? Plus it's like,
Hella cheap.
yeah. Plus like, all pizzas are generally the same. Wings, you get like a lot of variety.
Yeah, you
Just
just
like
throw.
versatile too, you know,
Yeah.
like, a lot of variety.
Yeah.
Mhm. You're kind of locked in.
The variety for wings is just wing with sauce.
Yeah, different sauce.
I feel like if pizza didn't
The
exist,
sauce can
sliders
be
would be super
anything.
popular. Like mini.
Probably.
burgers.
Maybe sushi is like my
Yeah.
that stuff.
I imagine tacos would probably, like
Yeah.
street tacos would
Yeah,
like kick in
that'd be
real hard.
amazing.
But that's like basically pizza without the sauce and cheese. You just order it.
That's an interesting take.
That's what I'm thinking.
I mean, a taco's a lot closer to a pizza
I know if I've
than a
ever-
sandwich.
Never heard that take before.
Cheese, tomato sauce, and pepperoni on a flour tortilla.
Dude, I've done that before. It's actually kind of fire.
My mom used to make naan pizza when I was a kid.
Non-pizza?
It works,
That's,
yeah.
Dude, that
Fire.
sounds
No
so
way,
good.
really.
It works, man.
Was it good?
Yeah.
Sweet.
I used to love it when I was a kid.
Dude, naan is so good.
I've had that before. In California.
Naan pizza? No, we just did it because my mom was too lazy to buy pizza dough or make her own. So I was like, okay.
Okay, cool.
Is that in
Works.
the laptop?
From last year.
Oh.
Uh,
For some reason, I thought you had a giant beefy gaming laptop, like one of the chunky ones.
no, that's him.
Oh, right.
You're confusing them.
Okay. So now, how familiar are y'all with the diffusion process? A little bit. All right, cool. That's all. So we'll start from basic diffusion. So the main idea behind diffusion is, so you have an image. How quickly does that draw? Cool. Draws quickly enough. So you have an image, and basically what you do is you have a function, and the function is going to add noise to this image. So you add a little bit of noise to this image. Let me get this here. So you add a little bit of noise, and I'll just draw a few red dots on there.
You're recording, right?
Yeah. Yeah, thanks. Oh, it doesn't show it up there. It shows it here. That's kind of cool.
Yeah, that's what I was wondering. I was
Yeah.
like, I didn't see that.
Yeah, you can see it. You can see it at the top. It usually has a bar at the top right. Yeah, that's cool. So it's called as t is equal to 0. This is our original image. Or t is equal to 0, and we'll call this x0. T is equal to 1. We'll call this x1, and we're going to call this function, say, p. So p is going to take in an image. So x1 is equal to, say, p of x0. And then t, so it just adds a little bit of noise to the image you currently have. So then we do this again, another time. So I'll take this image, and then I add a little bit more noise to it. So add a little bit more noise to it, and the image starts to go away, and the noise part starts to become very apparent. So this is t is equal to 2, and this is x sub 2, and you do this a bunch of times. So you do this over and over again, and eventually you end up with an image that is all noise, and we'll call this t is equal to t. Paste. That way, I don't even need that. So this final image is going to be 100% noise. So this is just noise. So at anywhere in this process, you have, I'll call this t is equal to 1,000 because 1,000 is pretty standard. So after 1,000 steps, you basically have all noise in your image. So this is x sub big T. So anywhere in this process, it's not that noisy at the initial time step, and then at the end, it's very noisy and it's all noise. And you can actually get any image at any time step through an interpolation between the original image and some noise. So we'll go ahead and do t times x0, or this will be big T minus t times x0 plus, yeah, I think that's right, plus, plus t times epsilon. And epsilon is going to be sampled from a normal distribution with mean 0 and variance 1. I think that's right. So that's times 0. This will be 100%. Yeah. And then you can normalize this, but it's easier to see this way. So basically, at time step is equal to 0, you have no noise, and you have 100% of your original image, x0. And then at time step, t is equal to 1,000, or t is equal to big T, you have 100% noise and no image. So that's just the forward process. So you have this chain. Anywhere in the chain, you can have a very noisy image or a not so noisy image. Now what we do is we train a model to reverse this process. So we train a model, we'll call this p theta or q theta, which will reverse this process. So at any time step, the model is going to give us the image at the previous time step. So q theta, q theta, q theta. So q theta, basically at any time step, is going to return the image at the previous time step. So let's say x sub t minus 1 is equal to q theta of x sub t, and it also takes in t. So this is our model, and the model basically gives us the previous time step. So given this noisy image here, the model is going to return this image here. Given this image here, it's going to return this image. Now that's a really high-level overview of what's called pixel diffusion. Basically, you're doing this in pixel space where you're just adding noise, and the noise is sampled from a Gaussian, and you keep on adding noise. So that's the idea of pixel diffusion. There's a lot of different things that are added on to pixel diffusion. So you don't actually have the model predict the image. You actually have the model predict the noise. So let's say if the model was given this here. Actually, I'll do this one here. So if the model was given this image, and you throw this through, so you throw this through the model, then the model is going to return all the noise in this image. So if I just erase everything in here, then it'll return the noise, and that's more stable. So that's what our model does. The model, given an image, it gives you all the noise that it thinks is in an image, and then you can just subtract that out. So the way you train this model is you give it an image, you go to some time step in the middle. So you sample some arbitrary time step somewhere in the middle of the process, and then you train the model to just predict the previous time step. So this image here, or this image here is an image at time step 1. So if this was a batch, you can imagine this is a batch. Instead it's just one image here, but you can stack them together and have a batch. But this is the model. So the model takes in this image, it takes in the time step 1, and then we train it to predict the noise in the image. And you just do this through mean squared error. So it's the mean squared error of, so our loss is equal to the mean squared error of our image at time t, so x sub t, where t is equal to 1, and also, and then the predicted output, so q theta of x sub t given t. So oh, this is epsilon. So you just train the model to predict the noise, that's all you're doing. And it becomes apparent what the model is actually doing if I expand this out a little bit. So q sub theta of this part here. Move that down here. And we'll just leave it at that. So basically all the model's trying to do is just remove the actual image part of the image and then give you the noise. That's kind of what the loss, that's kind of what you're training the model to do. So that's all you're doing for pixel diffusion. Now in reality, what you actually use is a stochastic differential equation. And we're probably not going to get into, you want to talk about stochastics? Yeah, nobody wants to talk about stochastics. But basically you use a stochastic to give you some image along this series of time steps. So this actually isn't, so we discretize this and do 1,000 steps, but it's actually a continuum where your time step is anywhere between 0 and 1. And you use this formula here, normalized in some way, to give you an image, to give you an interpolation between the two at any time step. So yeah, you use a stochastic. In reality, you don't discretize it, but it's a lot easier to visualize it discretized. So all you're doing, adding noise to the image, training a model to unnoise the image. Does that all make sense? Cool.
Don't get too stressed about the stochastic stuff. It's not.
Yeah.
It's just a
how you do
different
it.
perspective.
It's just this process, but a mathematician decided to take it and make it stochastic.
I mean, there's some cool things you can do with it, but for our purposes, not that important.
You use the stochastic, and then you reverse that with an ODE, and that's how you make it fast. So to sample from this
You can
model,
get fast sampling.
Yeah.
Basically.
and to sample from this model, what you do is you take your pure noise. So you take your pure noise here. So this is Z sub t, and Z sub t is just your Gaussian. So Z sub t is all noise. And because Gaussians are cool, you can just sample from a Gaussian with unit variance, or just a Gaussian from like that. And then you throw this through the model. So you throw this through your model, assuming it's trained. So this is inference after you're done training it on a ton of images, like a million images. And then it predicts the noise in the image between the time steps. So this will give you big T minus 1, so step 999. So whatever that may look like, a slightly less version of the noise. And then you throw this is step 1,000, this is step 999. And then you take the output of that, and then you throw it through the model again, and then you get step 998. And then you throw it through the model again, 997. And you do that 1,000 times to get your output image. So you just iteratively throw the image back through the model, given the noise. And that's why you train the model on different time steps, so that you can give it this, it'll reverse the chain one step at a time, and it gives you an image according to that noise. Now, since the noise is infinite, it's going to give you something that didn't exist. So it's not just copying whatever you had in there. A lot of people think it's just copying. It's not doing that, because if it was copying, then it would be useless and it would just give you your data back. It's not what it's doing. It's given some noise. It's creating the image that most likely corresponds to that noise according to the training data it was trained off of. And because it was given a ton of noise, it produces some image according to that noise. Now, I mean, that's kind of arbitrary. Yeah.
Now, at some point, you can introduce some sort of random seed, I guess?
Yeah, so the random seed will be, what you normally do is you introduce the random seed here. So you're sampling from a Gaussian.
How you initialize.
Yeah, it's how you initialize. So so you initialize it, and then that's the noise you add. And reversing it doesn't require any noise. So you initialize it, and then you just you just do the reverse process, and then that gives you your image. So that's the seed. So given the same seed, you get the same randomness, and then that gives you the same output. Now for text. So text, what you do is you just give the text to the model for a transformer, using a transformer. And actually, we'll get into text later, once we go through the latent diffusion model. So because they actually introduce it there. So we're going to introduce text later, but
Yeah.
real quick, basically what you do is you condition the model on text. So this could be like a picture, a cat.
Be
And
prepared,
then
the
you can-
conditioning is going to be really disappointing.
Yeah.
But it works.
It's just as disappointing as if that happened. You just throw it in the model, and then it works. Yeah, so that's pixel diffusion. Now, pixel diffusion is expensive. So imagine I wanted this to be a 1024 by 1024 image. Then it takes forever to process that, because you have to do the convolutions. So you use a convolutional neural network, and a convolution over a 1024 by 1024 image is it's really slow because it's a massive image. And if you want to go further than that, I think Excel uses 2048 by 2048. It's even slower. So to go around that, latent diffusion models do not do that. So what latent diffusion models do is they first introduce this encoder-decoder, so an autoencoder. So you have your encoder and you have your decoder. And what you're going to do is you're just going to train your encoder and decoder on images. So this is before you do any diffusing. So you have a encoder. Let me zoom in here. So you have your encoder here. And your encoder produces some latent representation of your images. So this will be a latent representation of the image. So this can be our cat. That's whatever, good enough. So this can be our image. You throw that through the encoder, you get your latent, and then you get your output through the decoder, and it's your reconstructed form. Now this is just another convolutional neural network. So you just throw it through a convolutional neural network. It downsamples the image to this small representation, and it essentially extracts the features out of this. So your image has 3 channels, RGB, and your latent is going to have a lot more features to it. So you can think of R, G, and B as 3 features of your image. This latent space has a bunch of different features here, which are arbitrary to us, but it basically represents the image in a compact manner, and the decoder reproduces the image from this. So the latent space has to be really rich with information if the decoder has to be able to reproduce the images. So this latent space is really rich with information, and that's why I use an autoencoder. But it also downsamples the image, so it's much smaller and it's much more easy to work with. So it's a lot more information rich, allowing the diffusion process it works better because it's information rich in the latent space.
It also makes training's a little bit more stable.
Yeah, because of the feature-rich information.
Feature-rich, yeah.
So.
But that
without the
assumes that
encoder.
you've trained your autoencoder well.
So X.
And that's why these guys throw pretty much everything you can at an autoencoder.
So yeah, let's go to the loss function. So this autoencoder is just a convolutional neural network. It downsamples it and then it re-upscales it. And the loss is basically reconstructing these two. But you want your latent space to be as good as possible. So let's go to loss. And it's actually kind of interesting what they do. 29.
If you just train on reconstruction, then you're not going to get a nice lane space. And if you get a nice lane space, you can't do it.
Yeah, you basically need a nice latent space because you need to represent the images, like they need to be disentangled. The latent needs to represent a unique image pretty much. And to do that, you need to have multiple losses. You can't just have reconstruction loss because the latents, there's nothing constraining the latents to be good. They're just
you'll
there.
have a latent space that's not continuous.
It can be good enough, and the decoder can deal with it.
If you
so
just
it
do
doesn't matter.
reconstruction, then
Yeah, so reconstruction is, so we've given our encoder and decoder reconstruction. This is our first loss. Loss reconstruction is equal to the MSE of x and x tilde, where x tilde is MSE x, and this is the decoder of the encoder of x. So that's just your reconstruction loss. This is pretty simple. You have your encoder and decoder minimize that. So that's the first loss. Adversarial loss. So how many of y'all know about GANs? Cool. You don't know about GANs? All right. So basically, a GAN. So you give it an image. This is basically how you would produce images before diffusion. So you have your set of fake images. Actually, I'll just draw that like a database. I don't want to draw an image. So yeah, good old database. I don't want to draw images. So these are your fake images. Not your fake images. These would just be your images. And what you have is you have a generator. So the generator, I'll move that over later. So you have your generator, and your generator is going to produce some image, and so this will be some image. This will be our fake image, and then you have a real image here. So the real image is what you want the generator to produce, and you throw this through a discriminator, and the discriminator takes in these two, and it outputs a value for each of them. And what the discriminator wants to do is it wants to maximize the difference so it can distinguish between the two. So to make this easy, let's say the fake is -1 and the real is 1, just to make it easy. So the discriminator wants to differentiate the two. So it wants to say the real one, like given an image, the real image it classifies as a 1, and the fake image it classifies as a -1. So let's say I had the Mona Lisa, that's real. Let's say I draw the Mona Lisa, that's fake. It can do a pretty easy job with that. We want our generator to do the opposite, where it wants these values to be as close as possible. So let's say 0. So the generator wants the fake image to look as real, as the real image. So it basically makes these two have the smallest difference, while the discriminator maximizes the difference. So, and this is all according to the discriminator. So the loss is over here, and you back propagate through the discriminator to optimize your generator. So the generator is optimizing the discriminator. Or optimizing, yeah, and the discriminator is kind of your loss function. The discriminator kind of says, is this fake or is this real? And eventually this should converge to a state where the discriminator is like, I have no idea, and the generator is producing images as good as the real images. Now this sucks because you have, it just sucks. There's a lot of problems.
That's the main thing. They're really difficult to train.
Yeah, in theory it works well. In practice, it does not.
It seems like the idea of like find the difference between two images. You want to get as close as you are to it, cannot find the difference.
Well, the generator wants to get the images as close as possible, and the discriminator wants to learn the difference between the images as much as
The
possible.
main issue with cannons is that there's no guarantee that there's actually no definition of converging, like not
Yeah.
really.
Right.
So there's no like, with pretty much every really good deep learning method, there's a curve that goes down, and the further down it goes, the better you're doing. But with cannons, that's not true.
Yeah.
Your loss can drop and be almost 0, and you can have a completely garbage GAN. So your
Losses don't mean anything.
Yeah.
Yeah, because basically the loss, there's two losses. You have one loss, and that's the discriminator trying to differentiate between the two, and you have the generator, which is trying to make the real image look as much as the fake
Usually
image.
what ends up happening is like the images that you generate with the GAN end up all looking exactly the same. Like you'll get the exact same image.
Oh, I see.
Yeah.
Yeah, it's called mode collapse, but yeah, that's
This on
pretty
paper
common.
looks like it's gonna work.
Yeah, it looks like it's going to work, and it did for like
It
the
does work well, it's just
MNIST.
hard to get it.
It's hard to train.
There was a model called Big GAN which did a pretty good job. It can compete with Stable Diffusion. At least it could during the time. I don't know about now.
Yeah,
It could compete with Stable Diffusion
For a brief
pretty
window of a moment.
whenever one was out. Yeah,
Yeah,
You say GANs are not good for images.
they're not good for anything.
For anything.
they're
Even
hard to
for-
train.
Yeah,
They're just really hard to train.
Even for agent behavior.
yeah. If agent.
No, there's a little bit.
Okay.
It's not that much. It's like usually just use a reinforcement learning, like PPO. You
But
just throw
that's-
PPO at it.
Because reinforcement learning also doesn't have really good.
They
definition
both
of
are.
convergence.
They both don't converge well.
Yeah. So there are some situations I've seen GANs do better, but in general, like for agent environments, you'll be doing a lot of RL first, because the way you train an RL is by kind of pushing it the right way, and the same thing with the GAN. But you'll learn more about your environment and where you need to kind of guide the agent's behavior to with RL faster than you will with GANs. Because GANs, you're kind of taking care of two things, and with RL, you're just.
Yeah. I mean, if you
just
think
have
about
rules
like
or-
what the optimization problem is, and like there was like tons of research in making it easy, but because like that discriminator chain updates and the generator updates, you're optimizing in this really like difficult space. And even if you try to do interesting things with the loss function, it's like there's no way to make that like a super easy thing to train. Like it's never going to be super stable. So that's the main reason this is a lot better, because it's a lot more straightforward to train. Stability is the biggest issue with GANs, in my opinion.
We'll call this negative and not positive. Yeah, so basically this is what, I think this is like a basic objective. So you want the discriminator, which has parameters theta. Does that look right to you? I think I got that right.
That's right.
Yeah, so you basically have your discriminator, which you're optimizing theta. So theta is maximizing the difference between the two, and beta is your parameters for the generator, and it's trying to minimize the score of the discriminator. So it's basically this mini-max objective in a way. One's trying to maximize the difference, one's trying to minimize the difference, but the generator only has control of what it generates. The discriminator has control of both of what it sees. So, but yeah, this runs into issues because it's not intuitive. You look at the loss curve and you're like, looks like a
It
loss
doesn't
curve.
mean anything.
Yeah, like you usually want it to go down, and it may not go down. It may just go like that. So the biggest problems is the discriminator could end up being like, this is clearly fake, and then the generator doesn't learn anything because the discriminator is like, this is obviously fake. So it has like the discriminator is basically your loss function. If you have a bad loss function, then you don't learn anything. So that's what you end up with. Or maybe the generator's too good and the discriminator can't differentiate.
Usually it's like the biggest problem is when you start training, like your discriminator is really going to easily be able to tell that these two are different
Yeah, so
because
you
you
kinda have to
randomly
stop it.
initialize your generator. So these distributions, if you want to think about them that way, they're disjoint, right? There's no overlap, and that makes gradient-based training really hard. And there were some things like Wasserstein distance was kind of meant to fix that.
Under 100 assumptions.
That has like so many assumptions, dude. It's probably not even Wasserstein distance, honestly.
Probably isn't. No, there was a
on
paper
how it
about
wasn't
it.
Wasserstein distance.
But yeah,
But-
so they're hard to train. And also, if you think about it, if you're the discriminator, how easy is your task? It's easy. You're like, this is fake.
Especially when
this
you
sucks.
start out.
This is not fake. This is amazing. And then the generator is like, I don't know. I'm trying to generate stuff from nothing. So it's really hard for the generator. It's really easy for the discriminator, and you kind of have to stop that. But there are some things that came out of it which are good. And
That shows
the
like
second loss is this adversarial loss here.
Yeah.
So if we treat our, so if you add more loss, if you add another loss to it, you're hoping to make the latent space
So-
better.
It's quick question. So
Yeah.
is this like, for example, we're saying it's bad because it takes a long time, because it seems like if you give it an infinite amount of time, eventually the computer can come up with something that's gonna work.
No, so in theory, yes, but the discriminator, like the gradients may be bad, so the generator just doesn't learn at all.
So it just creates the same thing over and over again.
Yeah, basically it doesn't know how to change its output. Like that's like you trying to draw some like the Mona Lisa and
It's
me
like
just
the
saying it
gradient
sucks, and
is
then you're like, I don't know
uniform.
how to
So
make
it's
this
like, what do you
better.
do?
You draw a new one, small changes.
Yeah, but then I
That's all the guidance.
but there's like no guidance to it. Like the discriminator kind of
makes it hard.
guides it
Okay, I
in a
see.
way.
Yeah, and that's why the Wasserstein stuff showed up. It's like if you think about the original GAN objective, if you like, there was a paper on this, but it literally like if they're disjoint, there's something called JS divergence, and it's a symmetric distance.
Oh, no.
But the problem with that is when you have distributions that have no overlap, there's no gradient. It's a
Oh, I
constant.
see.
So when there's
And
no
so
overlap
there's
at
no
all.
gradient. So what's the generator going to do, right? And so Wasserstein distance in theory, like it's a smooth. It's like the distance between, it's called Earth mover's distance. So if I have two distributions and I have move like
It's like
stuff from
moving
this
boxes.
distribution to this other distribution, like how much stuff am I going to have to move?
I think it's stuff
Basically.
and effort.
Yeah, stuff and effort. So that's nice because even if your distribution is just disjoint, you can still have like a distance that can change. Right?
But it still also sucks. Wasserstein. It's the best.
It's a bit better.
It's
It
the
actually
best, but
shows
it's
up
not.
here. They use it for their adversarial loss,
Which we're not gonna like look at that. Just the basic idea is good.
but they use it
Yeah.
for the autoencoder.
It's the same idea. Just
they use
different
everything
laws.
in their autoencoder.
Yeah. So
This is what it kind of looks like.
for the
So it's supposed to be generating
made a
the
question that might be
gold digits, but
confusing.
C just
Yeah.
generates like the same thing.
Remember when they were doing,
And it's
they were
basically
using
just
AI
like
for
when the
Dota,
discriminator
the video game?
Yeah.
You create something in the
Do you
discriminator
know if they
after
were
a long time of training. can't
using
distinguish
the normal human
Yeah.
graphical
So what
interface,
ended up
or were they
happening
just
was
taking,
generator
they had a different client that was interpreting the
like,
data?
that is
I think they took the GUI because like it would be unfair for them to not take the GUI.
rather than creating a realistic
So they were like actually playing.
Yeah, I would guess, because like it wouldn't be that cool if they just had like the input in some other way. It wouldn't be as cool.
So I was just thinking because
So
they
they're just
they
good
were
at
just
tricking the discriminator.
working at a
So-
logical level.
Yeah, I understand how
Yeah.
They could actually accelerate almost
Yeah.
to where the
Exactly.
I would imagine it was just the image. I don't know. I would look it up.
Almost your initial assumption. What if you give a slight little assumption to
You still run into weird issues.
Yeah, you always run into weird
It's
issues.
mainly just because like, you,
Cans.
as a
Cans.
researcher, you have to sit there and watch the outputs constantly, and then it's.
But they're also unintuitive
Exactly.
to whenever you look at them.
It's just fun to know.
Okay.
But with like diffusion,
It's a clear. It's just MSE.
there's a there's a ground truth.
Okay.
The right answer is the image you're trying to produce. Here, you're optimizing the discriminator.
So there is a possible world where GANs are far better than diffusion, but to get to that point requires a lot more labor and effort than with diffusion.
Okay.
Yeah.
No architecture is like necessarily better out of the box, but it's far easier to get diffusion work than it does GANs.
Yeah. Even though it takes a little bit longer to generate, it's better in the end.
And at this point, they're pretty much faster anyway.
Yeah. It only takes a few steps. Yeah. What's up?
Well, Tom, you mentioned in this like an ODE earlier.
An ODE, ordinary differential equation. Don't worry about it. But basically, that's how you're solving. It's basically like a path. I'll show you like an image to kind of give you an idea. But so if you think about it, you have your distribution here of images.
Yeah.
So let's say this is our distribution of images, a Gaussian. I drew a Gaussian. It's not going to be a Gaussian. It's going to be something in 1024 by 1024 dimensions. This is one dimension, so minor PCA. So basically, this is our image distribution.
Gaussian in 2024 by
Yeah.
2024 dimensions.
Yeah, this is our 1024 by 1024 Gaussian. So this is maybe our cat image here. Beautiful. And well, actually, it would be down here. It would be that part there. So let's say that's our cat image in our 1024 by 1024
Like how you were
space.
so like, no, it's definitely here.
No, it was on the Gaussian. That doesn't make any sense.
Oh, okay.
Yeah. So no, it's definitely here. So basically, your SDE, it's a noisy ODE, and it's just like it's a derivative path. It's like a flow. So this defines a path from your data distribution to your noise distribution. So this is your noise distribution. This is your Gaussian 0, 1. And your SDE defines some noisy path. So you start with very little noise, and it's some noisy path. So you start with little noise, and then you end up with large magnitudes of noise, and it ends up somewhere on here. So you just have this noisy path that it follows.
Okay.
Now an ODE,
The reason it's like different is because of that stochasticity.
yeah,
It's not actually like a derivative, but
close enough. Basically,
you can kind of
skirt
skirt around it
Yeah, sure.
a little bit.
Yeah, you can't take a derivative.
Yeah, it's not differentiable.
Yeah.
It's
That's-
not
You have
differentiable.
to define it in a different.
Well,
Yeah.
you can discretize it.
You don't
Or you
calculus.
can just
Yeah.
that one or the other one I always.
Usually you discretize
Or you
it
can just
using
discretize
the.
it, which is the cheap way of doing it, and then you just so there's a method called Euler Maruyama.
Yeah.
Maruyama.
Mariama.
There's
I think that's it.
multiple. Yeah, it's Maruyama.
That's the main one. Everyone
That's the
uses
main
that.
one people use because it's just Euler method for. So Euler method is a ODE solver that basically, I mean,
The
ODEs
Everyone
are just
uses.
like they're basically just functions, right?
Well, I was gonna show that real quick. The ODE.
If you're gonna show it then.
Well, like I was just gonna show that. Like, what does an ODE kind of
Okay.
like? Unless you want to.
I can like if you want to draw it, and I can just explain it.
Yeah. Let's do that.
Basically, ODEs are ordinary differential equations. You're given when you want to solve them, you're given a differential. So like y prime equals
So you can
lambda
discretize
y.
that.
That's a really famous one called the Dahlquist test problem. But they're all going to be like y prime equals something, or you maybe have y double prime equals something. Those are differential equations. When you solve them, you want to solve for y. Like what is y? So when you're solving them, you're trying to plot y. You want the real like what is it going to be, right? So for solving them, if you've taken an ordinary, sorry, if you've taken a differential equations class, you have to solve them analytically, and it's like a huge pain in the ass. And all of them are like different, and they all take different methods, and it's terrible. But then some really cool guys came along and they're like, okay, we're gonna make some numerical methods for this. And there's a class I'm taking right now, actually, where instead of having to solve these analytically, you can actually just plot the ODE by time marching. So you just take little steps along the x-axis and you plot the y as you go, and it just accurately plots the y that you have. And the really famous method, so the base method is called Euler. There's a forward Euler and a backward Euler, and then there's an implicit Euler. Forward and backward Euler are like explicit methods. So you're given a time step, you solve the next time step. So similar to what we saw earlier with the Markov chain. So you're time marching. That's what they call it in mathematics. So you time march all the way to the end, and you get your nice curve. And then backward Euler is just the opposite way. Implicit, however, is if you want to solve that, but you don't want to solve it by just time marching. You want to solve the entire thing by solving some linear system of equations. And the reason why you might want to do that is for stability, but I'm not going to get into that. Going to stochastic differential equations, since they're not differentiable in our regular calculus, you have to move them over into either Ito calculus or the other one, which is a stochastic calculus. But we don't want to do that, so we use
really
time marching methods.
unintuitive.
Again, we just use numerical
Quadratic
methods.
variation.
And Maruyama came along and was like, okay, I like Euler method, but let's make it stochastic. So there's a ton of methods that are
It's kind of
numerical methods,
interesting
like the
when it
base
clicks,
numerical
though.
methods,
You're just like,
but specifically
kinda
for stochastic ones. So you'll
Stochastics
discretize
are
the
pretty
space,
useful.
or you'll take a point and you march it across. And that's basically all you're really doing. It's not that complex, and you get a lot of bang for your buck.
Yeah.
And usually it's
I mean, basically, if
not
you don't know
really
how to
that
model it, you just throw an SDE
computationally
out of it.
costly. There's different methods that have higher orders. So order means like how good is your method? So you have a really high order method, it means it's really good. But usually with high order methods, your cost is going to be a lot larger because you're you're predicting way more accurately. So you're going to have, there's like a cost versus accuracy trade-off. With everything you always have that. So there's different methods for doing it. Euler-Maruyama is actually like the worst method for stochastic differential equation modeling, but
We love
it's
Euler, though.
really easy to use, and it's literally just time marching. So you just put in a point and it gives you the next point. So it's really, really easy. So researchers are just like, hey, I don't know a lot about this like stochastic differential equation thing. So why don't we just use the easiest one possible? And then they just do it, and it works. So
It's a whole
that's
paper.
good for them.
Is it?
I forgot which paper that was. Was that
Machine
InstaFlow?
learning research, you just kind of like bang.
Oh yeah.
Yeah,
Oh
a
yeah.
lot
Pretty
of
much.
machine learning research is literally just like, oh, I've heard of this
Trash
before,
it.
but I don't want to research it because I like machine learning more. So I'm just gonna put all this random crap together, kind of know what it's about, and then, hurrah! It has 99% accuracy.
Well, actually, this one, Song, he actually knew what he was doing.
Oh yeah, I'm
So the
sorry.
person who made this actually knew what he was doing.
Yeah.
Song,
Smart guy.
the Chad.
That
guy's cracked.
literal super genius.
Yeah.
I actually have his article up right now.
Usually when
Reading
reading
his autobiography?
there will be
No,
a
I'm reading
based
the
on percentage
score-based one right now.
based
Oh,
architecture.
Are you reading that right now?
Improve on
Because
it,
I have
it's a lot of
to-
habits.
Oh, okay.
For what?
Yeah, exactly.
Pretty much.
The people who designed transformers
sick.
for
Yeah.
LLMs,
It's
geniuses.
for my.
And it was like
that-
really
that class
smart,
I was
and
just
then
talking
built
about.
up on a lot.
I'm
It's
doing
not like a
my-
super
my,
complicated architecture,
final
but it's
project
still
on
like
stochastic differential equations and
foundation is very
numerical
solid.
modeling, and then
But-
Everyone uses that now.
Yeah.
That's it.
But,
Just change it a little bit.
Like the way people will train
machine learning
LLMs
about
today is a
that.
lot of
Would that be
hacks.
so cool?
Yeah.
It's a lot of
Which
weird.
ones are actually
Yeah, somebody
Yeah.
tried this one time and found out
So
it
cool.
doubled
We'll have to
accuracy.
Oh, the Frankenstein LLMs?
Yeah.
How does that work?
Things that just don't make sense to do.
Oh oh my
really
god, I hate
well.
those, dude.
I think like unless you want to be
Get a
um,
PhD in
the
mathematics.
top.
No, I mean, like,
you'll figure it out.
They literally take an
You
LLM,
can really get
rip
away with
apart
just being
different
pretty
parts of
hacky.
it.
Yeah.
glue
You
it
could write a
together.
ton of papers by
And it
just
works.
saying, we tried something and it worked.
It worked.
Yeah, exactly.
Well, if you want to get a bunch of papers, probably just throw some math things at it.
Gradient descent is just cracked.
And a lot of
apparently.
times too, they'll like
Apparently
really
that works.
boast about how much mathematics and intuition and all this one behind it. And it's like a 2-line change.
Yeah, so just to
What?
say,
2-line
the
lemma.
machine learning people, they don't understand the mathematics either.
Really?
So, like,
Nobody
But
does.
they'll write the paper like they do.
Yeah, yeah.
Yeah.
Actually, they do,
Full
they
confidence.
have no clue what's going on. It's actually like a really big field in deep learning right now is these mathematicians trying to figure out what the hell is going on and why any of this works. They're like, okay, why does deep learning even work? Because they don't, I mean, the people who made it don't really know. They kind of just hope that things turn out the way
It just
they
works
want.
out because gradient descent.
It just gets gradient descent. it's perfect. Stuff like that. So there's a really big field where people are actually trying to figure things out like that.
It's just superior.
But anyways, yeah, so you basically have this image and you have this stochastic, so you add noise to it. But since you already know what noise you added to it, you can deterministically remove it. So you don't know what noise you're going to add, but once you add the noise, you know how to remove it because you already added it. So that's why I use an ODE to get back.
Okay.
So this ODE is kind of like a smooth curve that you discretize. So it's not noisy to get you right back to your image.
It's an approximation.
Yeah.
Yeah, pretty much. And you discretize this more to make it faster. So imagine I just did one step. So that'll be a lot faster because I don't have to put it through the thing a lot more. But if you have a really high dimensional space, then yeah, it's bad because you're just stepping somewhere and
What's bad?
taking one step. And that's basically a GAN.
Yeah.
At a point, you can kind of say that's kind of like a GAN where it just does one step. So it's a lot harder to do that than if you like refine something that you created. So it's a lot easier to take multiple steps, and the ODE works better with that. But yeah, SDE because to add noise and then you know how to remove that noise once you added it. So yeah, that's the ODE thing. Anyways, back to the loss. Yeah, so the loss for this autoencoder, you have this as your generator. So your generator is your autoencoder. Actually, your generator is this part here. My bad. It's this part here. Your latent space to your no, it is your entire autoencoder. Never mind. Yeah, this is your generator. So this image is the generated image, basically. Your generated image. So remember, again, you want this to look as real as possible. So let me move this down. So you throw this through a discriminator here. Sexy D? I don't know. I already have D over there. So this will give you your output. So yeah, sexy D. It's actually a less.
The Greeks are turning in their brains.
So,
It's called Delta or something.
It's a little delta.
I don't know. I don't even know it there. I don't care.
That's due to the single hair.
All right, so that's our discriminator. So you throw the input into the autoencoder into the discriminator, and this is your real image. And then this is your fake image, the output of the autoencoder, and you throw this through the discriminator, and that's the same thing as a GAN, except this is your generator, and you're optimizing the encoder and decoder so that it produces an image that's more real according to the discriminator. So it's just an extra loss term to make the latent space better. And yeah, this is the loss we showed before, where it tries to maximize the distance, the discriminator, and then the generator tries to minimize it. So it makes it look as real as possible. And then there's a regularization term, but you don't have to worry about that. It just makes the latent space a little bit better using like variation autoencoders.
Yeah. So like autoencoders, so variational autoencoders use these it's like a KL divergence term. It's basically like
How far is the latent space from the from a normal distribution? Basically?
from a normal distribution.
Yeah. So it's so that it doesn't like vary any of this weird distribution looking thing.
You get rid of the weird, because if you do an autoencoder just off reconstruction, it's not going to be nice, continuous, and smooth. So,
Right.
And then who doesn't love Gaussians? So
We all love Gauss.
yeah. So they have the KL divergence from VAEs. They have adversarial loss.
Adversarial, and then they have reconstruction.
And then they have
'cause
reconstruction.
That's the main thing you're trying to
Yeah.
reconstruct it. So they have all three of those, and that's what makes this latent space really good. You need this good latent space because we're going to optimize in that latent space. So yeah, that's a lot about the autoencoder, but you have to have a really good latent space in order to do anything useful. So you train this latent space once, you train it off a ton of images. Just throw images at it, you get this really good autoencoder. Now the next thing you do, so that's step one. You train this. Once you train it, it's done. So 2 steps of training. It's not the same thing. So now you freeze these layers. So these layers are frozen. You have epsilon and D, and yeah, that's your autoencoder. So you basically go from pixel space to latent space. And now what we're going to do is we're going to train a model in the latent space as opposed to pixel space. So this is just your diffusion process. So you take your image here. Maybe this would be your image. Gonna draw a cat. You can cry about it. That's your image. You throw it through the encoder, and you get out your latent Z. So it's not a vector. It's actually like a set of feature images. And then you noise this. So I can't draw how you noise the latent space because the latent space looks like noise to us. But I guess I can draw it by adding a little bit of red to it. So you kind of noise it a little bit. And that's what you're adding noise to. You're adding noise to your latent, not your image. So if we start here with our original latent, set time step is equal to 0, then we add a little bit of noise to it. I guess I can draw it in red. So you add a little bit of noise to it. And this will be time step is equal to 1. And then you add a little bit more noise to it, so on, until you get Z sub t. So this is t is equal to big T. Let me expand this. Z is equal to big T, or T is equal to big T, and then this is just your pure noise. So you train a model to reverse that. So you just train a model to remove the noise in the latent space. That's all you're doing. Same thing, same process, same training objective. Train a model, give you the noise in this latent with noise in it. So that's all you're doing. Yeah, same objective. So pretty intuitive, makes sense. Just doing latent space. Now to do that, you need to have this UNet. So what a UNet does is, everyone loves UNets. So a UNet was originally made for segmentation of medical data, but everyone uses it for everything now. So basically for your UNet, you have your image. Let's say this is of shape h by w. You then throw this through your first layer, we'll call this L1. And it'll output an image that is slightly smaller, so slightly an image with extracted features that is slightly smaller. So this will be, say, h over 2 by w over 2. And then you throw this through L2, so another layer, and then it makes it even smaller, but it adds more features to it, so you have more feature maps. So this will be h over 4 and w over 4, and you have even more feature maps. And then you expand this, so you kind of upsample these, and let's say this is L hat 2. So this reverses the process that you did for L2. And this will give you H2, get 3 here, W2, and then you throw this through, say, L hat 1. And then this gives you your output image that is of the same shape, but this will be the noise in our case. This is what we want the noise to be. So this will be height by width. And then you have these skip connections here, which you add. So basically you have this high level information here. This would be like cat, and this will be with a little bit of noise in it. And then this is your noise prediction. So this sends the high level information across. So this is all your UNet's doing. It's compressing the image down a little bit. And it compresses the image and blows it back up to extract the features out of there. And it's useful because it extracts the features. Yeah, this is just used in practice.
Those skip connections are just concatenations.
Yeah.
So it's just like you have.
It picks the features it
yeah,
needs.
you just add the original whatever image you have at the end, and then just keep going.
So that's all your UNet's doing. It's just predicting the noise. It takes this image, it compresses it, blows it back up. It's just a useful way of extracting whatever you want to extract. Like I said, it was used for segmentation. It's also used for image. It's used for image to image. So you give it an image and you get out an image of the same shape.
Yeah.
It's also used for upsampling. It's used for everything.
So these kinds of networks are called fully convolutional networks. I guess autoencoders technically fit in that too.
I think so.
But
it's also CNNs.
it's just convolutions. So there's no dense layers. They're not classifying.
Well, actually, this is not a fully convolutional network. This has attention.
Oh well, not the original UNet.
Oh yeah, the original UNet. So
yeah,
we have this UNet. This UNet can give us the noise from an image, but we want to condition this on stuff. So now to condition this on stuff, you have these. So if y'all are here for the attention is all you need, we went over how you do attention, and you kind of bring in this outside. So like we did, what did we do? English to Spanish?
Yes.
Or Spanish? Yeah. Okay. So yeah, you have like your English text. I think it's Spanish. Whatever. English to Spanish. So you have your English text, and you kind of want to put that information into the Spanish text representation, the intermediate representation. So it's the same idea here. So you kind of have an intermediate image representation, which you can think of as the Spanish text, which we are trying to produce. And you take this outside information that you're trying to condition it on. So we were trying to condition the Spanish text on the English text to tell it to tell it what text to generate. In this case, we're conditioning the image on stuff, so text, to tell it what to generate. So that's what you can see here. They condition it on a whole bunch of stuff, but it's easy to just think of it as text. If you can get it in some representation, like if you want to condition it on images, you can just use ResNet. If you want to condition it on text, just use a transformer or GPT. So if you have this representation of your modality, so images or text, then you can throw it through these layers here. These layers are called cross-attention, which we talked about in the attention is all you need. And you can see that it has the keys and values from this skip part here, or from this outside modality, and then the queries are from the image part. So I kind of wrote it out over here. Yes, so if you have your, we'll do this in red. So what did they write this as? Yeah, so J theta of Y, that's your input modality. So this is some input modality. This will be of shape n by dj. So let's say this is our text. Then this is m tokens, which are of shape dj. So that's just m tokens in with a embedding space of d. So m by d matrix, just a square matrix or rectangular matrix. Then you have your image here, which you have height, width by channels, and you can combine the height, width together and get a rectangular matrix as well. So this will be your height, width, and this will be your channels. So your channels are like your embedding dimension in your, I think it's height, width by channels. You can flip it, but basically your channel is your embedding dimension, and height, width is the number of those you have. You can also transpose it, and it does the same thing, but yeah, basically you just need to get these both in rectangular matrices so that this works. Arbitrary, yeah, just get them in a rectangular matrix. Yeah, so this is your input modality, this is your text, and this is your image representation at some time step in the middle. And as long as the dimensionality...
Clip?
Should we?
I don't think so.
No?
We'll mention it.
Okay.
But yeah, so...
Isn't that how they condition? I thought it
Yeah.
was, right?
Right, on a
Yeah,
vector.
they use clip.
But you can also use the transformer. Or
You can use whatever.
You can use whatever. Well, they use the
Facebook
output
has the
of
new
the-
one that has like 8 things.
Yeah.
You can use that.
But yeah, as long as you get this to some representation like this, then your queries come from your image. So you just kind of send this through a linear layer, and then you send your keys and values through a linear layer as well. So these come from your input modality, and then you can mix it up by the attention matrix. So the attention matrix is formed from your image representation and your keys, which are from your input modality. So this attention matrix, remember, in attention is all you need, that kind of represented how does the text relate to itself, but in this case, it's really arbitrary. It doesn't make any sense to us. You're just combining the information in this matrix, in this attention matrix. There's no satisfying explanation for why it works. It just does because of attention. And then, yeah, if the shapes work out, then everyone's happy. And the shapes do work out because your values are then multiplied by your attention matrix, which gives you the same shape. So basically, you're just conditioning on this by creating keys and values from your text representation and your queries from your image representation. It's very arbitrary why this works, but it does. You're just combining the information in some easy way. Yeah, I don't think we want to. Yeah, so basically I use clip.
Yeah, clip.
Clip,
Clip's not that hard to explain.
Yeah, it isn't.
Yeah. Clip is pretty easy and kind of stupid.
So what clip does is they use clip to kind of put this information in the model or into the model. So like I said, we need to encode this somehow, the text representation somehow. So what clip does is it takes in an image, drawing the same image, and then it takes in the text, so a cat, and it has two encoders. So let's call this encoder 1. We will make it like that. And
So you
then
have
we
a
have
text encoder and an image encoder.
We'll call
Your
it-
text encoder is some kind of transformer language model, and then your vision encoder is either like a vision transformer or a CNN.
Then they both output the same vector shape. So this will be a vector of shape D. And then you do a relationship between them. So this cat and its text should give you a higher relationship score. So the vectors should have a high similarity. They should have a low similarity if I were to say a dog. And if I were to send this through the encoder and then get out a vector, then these two should have a high similarity. So this should be high similarity. These vectors here. While this image vector here and this text vector here, it's not a dog, so it should be low similarity. That's all Clip is doing.
Yeah.
That's literally all you do to train Clip. You just train it based off these image and text pairs, and then you have these vector representations, and that's how you condition your unit.
And this does work if you have 800,000
Yeah,
image text
you
pairs.
need a ton of images because you use what's called a contrastive loss, where you basically have these relationships, and you form this massive matrix, which is mostly, you don't want these to be similar. So if you basically form this n by n matrix,
Yes, and you only want the diagonals.
yeah, you only want the diagonal to be similar, while everything else
should be low.
is not similar.
Yeah.
So you need a lot of information because most of it, like if it just says it's not similar, if it just makes them as dissimilar as possible, then it does a pretty good job. So you need a lot of data to kind of convince it to do a good job. But yeah, that's Clip. You use Clip to, or some variation of Clip to condition it. Yeah, so that is that. Yeah, so then you just use this along with your text to create your image. That's about it. I don't think there's anything else for latent diffusion
that's
model. Any question? Oh, so to generate an image, so to generate an image, what you do is you have your latents here. So your latents at time t are going to be, so you sample from a normal distribution, and this will be your latents at time t. So L sub t is sampled from a normal distribution, and you throw this through your model, and then you get out a new set of latents at time t minus 1. So you unnoise the latents, and eventually you get to these latents at time 0, and then you send this through your decoder. So these latents are then sent through a decoder, which was the autoencoder decoder, and then this gives you your image at time 0. So that's our amazing looking image. So that's how you train it. You train it, or that's how you do the inference process. You do the inference process all in latent space, and then you can decode the image. So that's all you're doing. Cool. Make sense to everybody? Awesome. All right, so now let's talk about the video latent diffusion model, which is actually pretty simple. So to start, they have this cool drawing here, which makes intuitive sense. So this goes back to the SDE thing we were talking about. Basically, you have your image, your images over here. That's your image distribution. This is your Gaussian. And so given the same prompt, this should be the same prompt. I don't know why it's not. But given the same prompt, so if you want to generate images, if you give it the same prompt, you're going to get a completely different output. And you can visualize this by the trajectories here. Notice how the trajectories end up in a completely different spot. So that's a problem. What they intuitively want to do is have a trajectory that slightly changes so that you get a continuous video like this. So you want your trajectories to end up in similar spots to get your video, because if they end up in random spots, then you're not going to get something interesting. You're going to get something like this, because they're completely, that's what diffusion does. Diffusion wasn't trained for temporal consistency. It was trained to produce images from text. So they want to add temporal consistency. And it's actually really easy to add temporal consistency. You just add a temporal layer. So remember how we had this attention layer, and we had these convolutions and we had the attention layer. Basically all I do is they add a temporal layer. So your input, instead of it just being, so you have your height, you have your width, and then you have your channels. So that's your original image. So H by W by C. You instead have T by that. So you have, like, if it was 16 frames, then you would have 16 times that image. And you do this in latent space because images or video is even more expensive than videos. So it's even more important to do this in latent space. So you basically train an autoencoder on images. You train a diffusion model on images, but then you add this temporal layer in there. And this temporal layer basically mixes up this temporal information shown here. So this is basically your batch. So you don't have convolutions between temporal layers. So if we look at like how a convolution works real quick, just to like show you how it extracts information. If we have this here, this image, and then we have multiple channels, and then we have multiple batches, you can think of, so this is one image here, and then you have multiple channels. So a convolution will extract, say, this information here, and it'll combine it into one feature. So this will output a single feature here, and then you do a sliding window across all this. But notice, this is just the image. There's no temporal consistency. Imagine we had another frame here. This kernel here, which is how we do our convolution, doesn't take into account this image here. And you can't just expand your kernel to 3D, but it's expensive to have a 3D kernel. So if this is our image, height by width by channels, literally all you do is you change the channels to your temporal information. So if we have T by H by W by C, you can just change this out. So you just swap these two. And now you have C by H by W by T. And then this becomes your temporal information, and then you have your kernel like normal. So that's what the temporal layer does. You're just doing a transpose, and then you add this in there, and you retrain your model on this video information so that it learns this temporal information. So you already train it on your stable diffusion. You already trained stable diffusion on images, and then you train it again on video using this temporal layer, and then you freeze the other layers. So like the spatial layer here is frozen. They do also use a convolution 3D, so they use a attention layer, and then they use a 3D convolution. And then they basically allow it to choose between the information. So you have this spatial layer here, which just has information of space. And then you have this convolution layer, which has information of space and time. And then you do a interpolation between those two. So if this was 1, then it would just be your spatial information. If this was 0, then it would just be your spatial temporal information. And if this is somewhere in between, then it chooses some spatial information and some temporal. So you just let the model learn what information it wants to pick. So all you're doing is adding temporal layers so that the model can learn this temporal information. So you can't just throw an image at it. It has to be able to look at the time information. And then you also condition this on text. So this right here, I think they just use a transformer, or they just use cross attention here. And then they use a 2D convolution. I think that's all they use here. So it's just adding the text information into the temporal spatial channel information. So that's all you're doing, just adding some temporal layers. Now, that's interesting and all, but they do actually do more to that. So that can only get you so far. And it's because like video is so hard to generate. But what they find is you can actually just generate keyframes and then interpolate that. So you only have the model generate, say, keyframe 1, keyframe 2, keyframe T, and then you just have a model interpolate those. So you have this interpolation latent diffusion model. So you actually have another diffusion model that takes in, I think it just takes in this image here, and this image here, like you concatenate them, and then you get out your next frames here. So you have an interpolation model. Yeah, these are just shared. So you basically have an interpolation model that takes in your 2 frames and then it interpolates in the middle. You want this interpolation model so that it can generate these frames in it's a quicker manner. So like if you were to generate them all at once, then it's going to take forever. But if you have a second model that interpolates it and the model is smaller, then it has to do less work, but it just has to generate some interpolation. I think it was just another model, right? Another latent diffusion model
For what?
for the interpolation. I think it was just
Yeah,
another,
it was just another.
it was just another latent diffusion model. That's all. That's all it's
Kind of
using.
dumb, honestly. It worked though.
It worked. So yeah,
Same thing with the
basically
resolution stuff.
Yeah, the resolution stuff.
Yeah.
Temporal fine tune. Yeah, here we go. So they take inspiration from cascaded diffusion models. So cascaded diffusion models is like given a diffusion model, you generate like 512 by 512 images. So you generate 512 by 512 images, and then you have another diffusion model that takes that image and then scales it up to 1024 by 1024. Then you have another diffusion model that takes that image and generates it to 2048 by 2048. So they do the same thing, except they do that for both the quality and they do that for the time. So they do the diffusion upscaling, like stacking diffusion models to interpolate the frames. And then they also do one more thing. So to have long-term generation, you can't just generate all the frames at once. So instead, they train it. So they learn prediction models that condition either 0, 1, or 2 context frames. So given 0, 1, or 2 context frames, it generates the rest of the frames. And this is just so that it learns if I have 1 frame, then I can generate the rest of the frames. So like if I go here, if I were to just generate these 3 frames first, then I can generate the next 3 frames by giving it this image here, and then I generate the next frames. So that's all they're doing there. And that increases the time you can generate. And yeah, and overall it's really simple what they do. They just add temporal information. Or they just add temporal convolutions, that's all they're doing. And then they do some weird tricks with it, but
And the attention layers.
yeah, and the attention layers. But yeah, if you just add temporal layers, it can generate video in somewhat decent quality. This one actually has pretty good quality.
Yeah.
What's up?
So how is this different from deepfake and how they're doing?
Defects.
Yeah, deepfakes. Well, like deepfake, it depends on how you generate the deepfake.
videos.
Yeah.
Usually for like a deepfake, well, this can be used for that, but usually for like a deepfake,
They take a set amount of like images and they merge it with something currently playing, but this is kind of like
Yeah.
Usually with deepfakes, it's like it's an easier task because you're not necessarily generating the video. but
you
you're-
usually have like a base video and then you just need to
Yeah,
change
usually-
it.
It used to be like that.
you're changing someone's face.
Yeah, but now they're not. They're doing it. It used to be all the faces for do the deepfake correctly, but now they're doing something like essentially where it's like you're taking a set amount of image and you're taking that and making a next image with that in mind. Is that what this is doing in a way?
Yeah, so
I thought
Temporally consistent.
Deepfaking was a keyframe matching.
That was it used to
Yeah.
be, but now they're having it so now you can
Oh.
actually extend beyond where you have. A
it's probably like this because it takes in a context frame and then it can extrapolate
Yeah,
that. So it's
okay.
probably like this
Okay.
because I'm guessing,
If it can do
You
that,
can-
it's probably this.
yeah,
Okay.
because if it's generating it good enough, then it's probably this where you give it 1 frame and then it can extrapolate that, or you give it 2 frames
Or
and it can
something
extrapolate
like
that.
this.
Okay.
Yeah, because this does that. It's not meant for deepfakes, but it can probably be used for deepfakes because of how you train it. You train it for long video, but you can probably give it a part of your video and then it can generate it longer. So that's probably like a method to do it. Yeah.
We're not encouraging deepfakes, by the way. So
Yeah.
Don't spread misinformation. That's our club policy.
yeah.
Wait.
I think they actually have some cool demos of this. If y'all are curious, this is an older paper. When I say older, I mean it was made like a few months ago, so pretty old, very ancient. back in my day, we had latent diffusion.
The other video papers aren't that good though.
Yeah,
though some of them
this was the
have-
most interesting.
Some of them have done better than this.
This was the most interesting, and that's why we picked this one.
Yeah.
Most of the newer video ones just change the interpolation, honestly. So if you see a lot of those stable diffusion videos and stuff, you'll notice they're really smooth, and the reason why they're smooth is just because they're interpolating, not because they're actually generating more stuff in between. So there hasn't been like any crazy jumps in the technology since this paper, but maybe it will come tomorrow. What do I know?
Did they?
I mean, there was some cool stuff where, like they combined pixel and latent diffusion, because latent diffusion can set the videos can sometimes have like artifacts. So I thought that was kind of a cool paper, but the results weren't like significantly better. Like they weren't like.
Oh, here we go.
But it was an interesting idea. Is that from this paper?
Yeah. That's from this paper. They're pretty good.
To be fair, at the time that this came out, I was really impressed.
Yeah, it's a lot.
This was a big jump in quality.
It was like the first ones that were actually like pretty good and consistent.
Like kind of cohesive videos.
Yeah.
Like it's.
They're not much better than this though. This is about as good as you get. But there was the car one, and the car was crazy.
The
Car one?
Yeah, the car was crazy. Look at this. They had like a 5-minute long video of this. Like this is pretty damn consistent.
Speaking of cars, I've seen like a synthetic data set of like environments like that.
Yeah.
Generated all of this.
It's probably like a variation of this because this was like the first one that got videos this good for cars.
So, like, I mean, they probably used a technique like this one.
Yeah,
to
yeah.
generate,
For sure.
Yeah, definitely. Yeah,
These were the
so-
first this was the first paper I can remember where I looked where like you
It was,
looked
like,
at the videos
impressive.
and you were just like, this is actually like
Good.
like you could fool someone.
You kind of have to like really be looking to
Yeah.
where it kind of like the car in front starts being weird, but even the trees. Are
It's
fine.
very consistent. That's
Yeah.
that's the like hard part. It's cool. Yeah. What do they got? They got a bear walking.
Yeah, see these moving
are not as
animations
good.
are so tough.
Oh, now it's going. Oh, this is not gonna be good.
Yeah.
It's actually not bad.
That's not terrible.
No, I thought that would be a lot worse.
Dude, yeah, walking and running are still just like it's really difficult.
The lighting is really good though.
Yeah, it's because all of it is based off the diffusion model, so the images itself are going to be really good, but the problem is like the interpolation,
Yeah.
the temporal consistency, because this only takes like 1 or 2 frames to produce the next frames. This one's pretty good.
Yeah, his hand. I remember the hand is like freaky in this.
I think the
Free
hands are going to
hands.
be a lot better now, because the hands are
Those are some of the artifacts that
from stable diffusion.
yeah.
Like the hands are the stable diffusion artifacts.
No, but like that's why that paper you showed me. That's why they were using pixel diffusion, right?
Yeah,
For
so-
those kinds of artifacts.
So yeah, pixel diffusion is actually better for. Pixel diffusion is actually really good, but it's really expensive. It's better for artifacts like hands, and it's actually better for text. So if you want to generate text on an image, it actually does a lot better with pixel because you don't have to compress it to this latent space. Like you can imagine text compressed to a latent space, an A latent may be close to a B latent. Because they're similar in how they look. Maybe that's what it found, because like text, it's not too much different from each other if it's like a black piece of text. But pixel diffusion has to learn that.
Yeah.
It can't remove that feature because the autoencoder, there is no autoencoder.
There are some papers that have come out where people have basically tried to merge pixel and latent
Yeah.
diffusion to get rid of some of these artifacts.
I think the
And
best
it kinda
thing
works.
I think the best thing will be to use a latent diffusion model to generate the image, and then use a pixel diffusion model to tweak it, because then you get rid of the hand
Yeah.
artifacts and stuff and the text artifacts. Yeah, that is this paper. Oh, cool! They got another cool animation.
This time that's cool. It's cool.
Who
I like
published
that.
this paper again?
This is NVIDIA.
NVIDIA.
This you want to know who did it? I bet it was Karis. I bet it was Karis. Is it not Karis? No way.
Not.
I'm disappointed. Where's Karis? Karis is supposed to do all the cool stuff.
Is that Seal like that song guy you were talking earlier?
Mm-mm.
A different
No,
guy?
Karis was the one who made like Staugan 3, and he actually made one of the samplers.
Really?
Whenever you use the
Style Game 3, bro.
Staugan 3 was crazy.
That paper.
Nobody understands
That
that
paper
paper.
gives me flashbacks.
Yeah, but he also generated a sampler, so whenever you're doing diffusion sampling, you see DPM plus plus 2M and then Karis.
Just kinda gave me
He just made him better. So yeah, this guy's kind of cool.
Game was like the coolest thing ever.
Yeah.
Everyone like lost their minds.
And then
Yeah.
Staugan, nobody actually knew about Staugan 3. People are like, whatever.
It's so weird how.
Style Game 3 is such a hard paper to read.
I still don't understand
Yeah.
how can you go from a discretized space to a continuous space without any loss. They're just like, yeah, it's magic. It works. How does that make any sense? Did you ever figure it out?
I have some ideas, but I never actually, because they don't really say it.
They had to have the most insane interpolation function ever. They had the best
It
interpolation.
has to be a numerical method. Like, just don't say what it is.
Yeah,
It's probably a 2D numerical method.
I don't know.
Or probably for ODEs, honestly.
You think they use an ODE to do that?
It always is. It always is.
Yeah, if anyone's gonna do it, it's Karis.
No.
Right, gonna
Nathan, I
end
know
the
you're
recording
talking about
here.
Style Game was like